Welcome to The Explainer. Today, we are digging into some pretty incredible life-saving engineering, the kind that's hidden underneath modern armored vehicles. It's this amazing story of brutal physics meeting some really clever geometry. It's the design revolution you'd probably never even notice from the outside, but believe me, it has saved countless lives. And really, it all boils down to this one simple question. How can a basic shape, we're talking something you probably learned about in middle school, possibly defeat one of the most devastating weapons on the modern battlefield? Well, the answer? It's just this surprisingly elegant bit of physics. This slide right here gets to the very heart of it all, the problem and the solution. See, on the left, you've got this flat hull. It basically acts like a launch pad, catching the entire force of a blast from below. But look to the right, that V-hull, it uses some pretty simple physics to push that same deadly energy safely away from the vehicle. Just a total game changer. All right, so here's what we've got on tap. First, we're going to get into the brutal physics of the problem, the box versus the bomb. Then, we'll see how a simple shape can actually save lives. After that, we'll look at the smarter materials and stronger hulls that make it all possible. And finally, we'll wrap up by looking at the future, which is all about centering the design on the human inside. Okay, let's jump right in. Section 1, the box versus the bomb. We really need to get our heads around the terrifying physics that engineers were so desperate to solve. So, what happens in an underbody blast? Well, when a mine or an IED goes off underneath a vehicle, it's not just some big bang. It's a supersonic shockwave, a literal hammer blow of gas and pressure. And for an old flat-bottom truck, this is the absolute worst-case scenario. All of that force goes straight up, launching the entire vehicle into the air, with so much violence that it can be lethal for the crew inside, even if the armor itself doesn't break. It's just a catastrophic event. Okay, so now that we've seen just how bad the problem is, let's talk about the solution. And it is a brilliant, physics-based idea that really did change everything. The V-hull, it's genius in its simplicity. It works kind of like the front of a ship, the prow cutting through water. So when that blast wave hits the angled hull, that V shape literally splits the force in two. Most of that violent energy gets pushed out and away to the sides instead of going straight up into the crew compartment. It's just a simple, elegant piece of geometry that manages to redirect an absolutely immense amount of power. And, this idea has been on quite a journey. It was actually pioneered way back in the 1970s in southern Africa with vehicles like the Casper. Fast forward to the 2000s, and the U.S. military rapidly adopted the design for their MRAPs in Iraq and Afghanistan. But, as you're about to see, the evolution didn't stop there, not by a long shot. Right, but here's the thing with engineering. Solving one problem often creates a brand new one. To get that deep V shape, the whole cabin of those early MRAPs had to be jacked up way higher off the ground. And this, of course, raised the vehicle's center of gravity. So suddenly, you had these trucks that were fantastic at surviving a blast, but were also dangerously prone to rolling over on rough terrain. So it was back to the drawing board. This forced engineers to innovate yet again. And the solution they came up with? The double V-hull, or DVH. The easiest way to picture it is like a W shape on the bottom of the vehicle. You get all the same life-saving blast deflection, but now with a much lower profile. This let the whole vehicle sit closer to the ground, which, as you can guess, dramatically improved its stability. And this chart here really lays out the engineering trade-offs perfectly. Look at it. The deep V-hull, excellent blast deflection, sure, but the price was a high center of gravity, a big rollover risk, and a pretty cramped interior. The double V-hull, on the other hand, kept that amazing protection but lowered the rollover risk and actually opened up more usable space inside. It is just a classic example of iterative design, solving one problem, then the next, then the next. But you know what? The shape of the hull is really only half the story. The materials it's made from, and just as important, how it's all put together, well, that's gone through its own quiet revolution too. Yeah, a modern hull is basically a layered cocktail of really advanced materials. The main structure, that might be something like Eglin steel, this super high hardness alloy. Then, on top of that, you might add ceramic composite tiles that are designed to literally shatter anything that hits them. And then, on the very inside, you have what's called a spall liner, made of Kevlar or Dyneema, and it acts like a catcher's mitt, stopping the hull itself from turning into shrapnel. And now, 3D printing is on the horizon, ready to change the whole game all over again. And this gets to the absolute heart of the next big leap. See, traditional hulls are welded together, And every single one of those weld lines is a potential failure point. It's a stress concentrator. So the ultimate goal, kind of the holy grail of hull design, is to create a jointless hull. A single monolithic piece with no weak points at all. Now, we're not quite at fully 3D printed hulls just yet, but automation is already making a massive impact. Just think about this. At BA Systems, some of the most critical long seam welds used to take a skilled human welder 32 hours to complete. Now, robotic welders get it done in just 3 hours. I mean, that's a reduction of over 90%. And the crazy thing is, the result isn't just faster. It's a stronger, more consistent weld every single time. But at the end of the day, all of this incredible engineering, the fancy shapes, the advanced materials, it's all completely useless if it doesn't protect the most important component of all, the person, the soldier, inside. And this right here is such a critical innovation. In older vehicles, the seats were just bolted straight to the floor, the very same surface that's taking the full force of the blast. This meant that whole lethal shockwave was just transmitted directly up a soldier's spine. The modern solution? It's so simple, it's brilliant. You hang the seats from the ceiling, physically decoupling the soldier from that floor blast. And that kind of thinking, it extends to everything inside the cabin. Modern designs have what they call floating floors, so a soldier's feet aren't even resting on the hull. There's carefully calculated sway space to make sure a helmet won't slam into the roof during the violent toss of a blast. Literally every single detail is engineered with human survival in mind. All right, now for a question that sounds like it's straight out of science fiction, but it's quickly becoming a reality. How on earth can a soldier see through solid steel? How do you give a crew total awareness of what's happening outside when they're sealed up inside a windowless metal box? The answer is something called the digital hull, and it's amazing. You basically cover the outside of the vehicle with cameras, use software to stitch all those video feeds together in real time, and then you project that seamless 360-degree view directly onto a display inside the crew's helmets. They can literally see through the steel hull. It gives them incredible situational awareness and, bonus, it gets rid of periscopes, which have always been a major ballistic weak point in armor. And what's cool is that all this technology leads to some really distinct design philosophies. You can actually see it in the final look of the vehicles. You've got Rheinmetall with its aggressive, almost futuristic style. Then there's General Dynamics, which is much more about that utilitarian, step-by-step evolution. And then BAE Systems often goes for this integrated, almost stealthy profile. The engineering choices they make end up creating a totally unique visual language. Which, of course, brings us to our final big question. We've spent this whole time talking about how hull design has evolved to protect the human crew. But what happens when the most important part of the vehicle is no longer human? As we start moving towards unmanned turrets and fully robotic vehicles, designers are going to be freed up to create even more radical hull shapes, optimized purely for survival. It's a revolution that really is only just getting started.